Hello everyone, my name is Andreas Benzing. I'm Executive Director of New York Passive House, and I would like to welcome everyone to our last product showcase presentation this year. Thermally broken shelf angles. It's organized by New York Passive House and presented by FERO. I would like to thank FERO for your support of New York Passive House. As a sponsor, we are very excited to have FERO as a strong partner moving forward. It is my pleasure to introduce Jose Herrera, New York Passive House volunteer, and Jose will introduce today's presenters.
And yeah, welcome to FERO, to the last product showcase. I would like to give a brief presentation on the presenter, Adam Kimball. He is the sales director. Adam oversees the sales and marketing of all FERO products through North America, with extensive experience in the built environment, from field to office in all stages of the product development. He holds a bachelor's degree in civil engineering and business administration and management. And he has more than 20 years of experience in innovative construction products. And I would also like to introduce Andrea Hatsinikilas, the president at FERO, and she will be moderating the questions. So at the end of the presentation, we'll be answering any questions or comments you may have, and hopefully expanding on the product. So with that, I'll leave it up to Adam and Andrea to give us a rundown on the product.
Jose, thank you for the introduction. Andreas, thank you for giving us the opportunity to speak here at the New York Passive House. Great organization, lots of experience with it in Europe, and glad it's seeing more and more traction here in North America. So thank you all for joining. I know this is a time where we can't all get together, so we do the best that we can with these presentations. I know it's in the midst of the rest of the work week, it's always difficult to find the opportunity to get to a presentation like this. So as Andreas and Jose had mentioned, what we're going to talk about today is our thermal brackets. And so what we'll get into is really on how to improve the building envelope, not only for Passive House, but also for projects that might not be looking for the Passive House designation, but are looking actually just to meet the building code in New York, because there are new regulations in the building code that started in May that is requiring you to calculate the shelf angle thermal conductivity in the building. So this is a great opportunity not only to learn about how the product can benefit you with your Passive House designs, but also just to meet the building code requirements in New York. There we go. So it is an AI presentation. We'll talk a bit about the product. We'll try to not be too egregious talking about fast thermal brackets. If you're looking for AI credits, feel free to reach out to us at FERO. We'd be more than glad to provide you those for this last minute rush to AI credits that you may be needing. So a little bit about FERO. I think it's important to talk about the company and where it's come from. So we've been a company based in Edmonton, Alberta, Canada, and it was created in 1995 by Dr. Mike Hatsinikilas. And so his intent was he's an adjunct professor. He's done lots of white papers and studies on masonry supports. He did this for the Canadian Masonry Research Institutes. And so when he came with the idea of how to improve the structural integrity, the thermal performance of a building, from an academia standpoint, it was not received very well. So he took the position of saying, hey, maybe I should get into the commercial side and introduce the products from that perspective. And that's the genesis of the company. And in the meantime, and during the duration since 1985, we started with masonry ties and connectors. And then we grew the business out of that to thermal brackets, which we'll be talking about today, and some other ancillary products such as fire release connectors, custom connections, and supports. So I would generally describe FERO as a company that has engineering, that does engineering with facade connections. So we focus mainly on masonry, but we also do get into other facade connections as well. So as myself as a structural engineer, and we have a large amount of people at the office that are focusing on engineering design. So we just don't sell materials. We actually do the engineering. We do a lot of delegated design work. So this is a lot of things that we take on from our perspective as a design engineering company that does a lot of delegated design for this. So the current Challenge. So first we'll talk about the challenges that we have with our designs with masonry. You know, we're coming into a time and age of where we're designing buildings and there's new code regulations, there's new, both from just a standard benchmark to more improved building envelope. And so with Passive House, that's the first challenge in and of itself, is to take the building envelope and make it as efficient as possible from the thermal and the air infiltration. And so we'll focus on the thermal perspectives from a wall assembly with our products today. And so the current challenges is now with Passive House and the requirements for continuous insulation outside of the envelope. We're now having to have structural supports for those things that generally have been pretty close to the structure of the building. So the current challenge is designing efficient masonry wall systems to meet those demands and expanding energy code and guidelines. So generally, brick is actually a pretty efficient veneer. You think about its durability, and that durability of a thick veneer has its benefits such as its thermal flywheel. It actually absorbs the heat and it transmits it during the period of time in which during the day when it's warming up, it transfers that throughout the evening hours into the building. So that's a common concept for masonry veneers. You see this in prehistoric constructions such as adobe houses, or you look at clay buildings that are from the eons in our history that are built out of masonry because of that effect, is this thermal flywheel. Designers are using increasing insulation thickness to further improve that efficiency. But larger cavity walls require large shelf angles, and shelf angles create a number of issues and challenges for the designer. And so what we see here, on a laser pointer, there we go, this fancy laser pointer. So generally we have here is your insulation, and then we have this large angle. And say 10 to 15 years ago, we wouldn't have this insulation here. The angle would be further back to the slab, closer to the slab. But as we add this insulation, this angle ultimately gets longer, and this is where we're causing a large thermal conductivity transmittance point. So the challenges of conventional shelf angle and design. So thermal bridging. That shelf angle, as we described here, is creating thermal bridging. A simple premise for thermal bridging is it's the mass and the surface area. So if the mass is great and the surface area is great, the larger the thermal conductivity that would happen in that location, and hence the larger thermal bridging that you would have to account for in your envelope. So thermal bridging here, and then you can see here just the size of this metal. It's ultimately becomes difficult to install. So large cavities require heavy and large shelf angles to be installed in this manner. It's difficult to adjust just by the sheer lifting of it. You have to think about a hoist or multiple men to lift it. And there's very small anchor points that are just being drilled through this shelf angle here. And lastly, and most importantly, when we're talking about masonry and when you're thinking about designing with a facade with brick, you have a heavy facade. And so this angle has to get bigger to support it. And this angle, as it gets bigger, it also gets more expensive. And so we have to start making adjustments of how this is going to impact the scope of the building. So first we'll step into thermal bridging. So shelf angle attached to the backing penetrates the insulation, providing continuous bridge from the interior to the exterior of the building. And so as I mentioned just a moment ago, so now we have a mass. So steel has the highest mass as far as a structural component that we can generally use. If we think about those components, we think about wood, we can think about concrete, and generally steel. Those are the tried and true general structural components that we use. Wood, rather low mass, lower conductivity comparatively, concrete being in the middle, and then lastly steel. And so we have that mass here in this location that is ultimately going to provide that first problem of that equation with thermal conductivity happening here. And then we also have the surface area. So the surface area is the linear thermal bridge. So we have it, this angle will run along the complete perimeter of the slab edge here to support your masonry veneer. And so these two variables in the equation of what creates a thermal bridge is going to be a huge impact to the building itself. So you can see here in this bit of a diagram that's provided by the IMI in 2020, you can see that this angle is a long, continuous linear thermal bridge based upon the mass and the surface area of it. And here you can see in a therm model that you're always trying to find the delta of where the heat is going to be managed. And so we can see here real quickly, we can see a masonry tie going through the insulation. So here's your insulation layer. The intent always is to have these thermal bridges find their delta within the insulation plane. But as we can see here, due to this large angle and its thermal conductivity due to its mass, we're finding its delta both on the interior plane of where the block wall would be, or here on the outside. And so we're having this large transmittance of energy through the whole facade. And when we have this large conductivity being transferred from the exterior, being it cold to hot in this area location here, this is when we can potentially, if the humidity is at its a high enough dew point, we can create moisture in this location, and moisture ultimately can cause mold. And so this is something that you have to consider when you're encountering these thermal bridges. So some people say, okay, well, that's theoretical, but how does this actually work in real life? And so this is a therm photo with a FLIR camera. And as you can see here, I would like to point out some benchmarks just for reference points. So you can see here on the right side of this building, you have windows. And then here at the top, you can see at the location of the parapet wall where most of the energy escapes throughout the building, you can see this is nice bright white. So the brighter the color, or the transition to a red color to a white color, will define the heat or the heat loss in that location. And so you can also see that here's probably a brick a CMU corridor or staircase that's in the perimeter of the building. But then we get to this location here, and we can clearly distinguish where actually the shelf angles are located in this building. And so some people would say, well, where's the masonry ties in this? And then we go back to that same equation that we talk about, mass and surface area. And so when you think about masonry ties in comparison to shelf angles, there are some gradients of heat loss, energy loss through those masonry ties. But ultimately, due to the relatively low mass and the surface area being punctual thermal bridges rather than a linear thermal bridge, it doesn't show up quite so clearly when you compare this to shelf angles. So here's a photo that we were able to use from RDH, which is a facade consultant in Canada, one of the leaders of the thermal energy modeling community, highly recommended, and one of the vanguards of this industry. Well, John Straub was the person that put this together. He's got quite a lot of documentation. If you're familiar with this gentleman, he's very astute in the areas of thermal bridging. And so we have here initially, this is probably the building that we might have been familiar with that did not have continuous insulation. And so for the sake of this, you can see here that we have a clear angle that's bolted to the slab. And so that's with no insulation to the exterior, where not only are we having a thermal bridge that's happening at the angle, but we're also having thermal bridges here throughout the studs of these cavity walls. So in this situation, there's really limited benefit because there's so many thermal bridges that are happening within the building that there's very little to try to solve in this location. So this is the real ugly situation. And then you have the bad. And the bad, what we're trying to now achieve is we have insulation here along the exterior. So we're eliminating the thermal bridges of your studs and your backup wall. But now this insulation, so we can all think to ourselves, what's the common insulation thickness that we're specifying? In New York, we generally see at minimum 3 inches. We're starting to see more commonly 4 inches. And so this 4 by 4 by 1/4 inch angle will now be transitioned to add that insulation thickness that you've increased that to. So if we said that this is now a 3 inches of insulation, so we have 3 plus the 3 5/8 inch brick. So at minimum, we would have a horizontal leg of this angle at 6 inches. And so we commonly see here, to make sure that you have enough space for your air cavity, we have a angle here that would be commonly 4 by 7. And so this would be the dimensions of this angle. And so if we go back to this one, this is 4 by 4 by 1/4. And due to the heavy veneer now being at the tip of this angle, and we'd want to resist the tip deflection of this angle here due to that veneer weight, we have to make this angle also thicker. And so now this angle that was now dimensions of 4x7 is also going to be 3/8 to a 1/2 inch thickness. So it's now doubled the mass. So we go back to that one part of the equation. The mass is now doubled from here, from 1/4 inch to the 3/8 or roughly a 1/2 inch in this location. And so ultimately what we want to get to is this situation. So now we still can have our continuous insulation, but now we are using an offset shelf angle, and the offset shelf angle provides your insulation that would run continuously, for the exception of the areas where it's being anchored back to the slab. So there are now punctual thermal bridges that are happening, but these are intermittent based upon the spacing. So next is installation challenges. As we kind of transition from the slide that we just spoke about, we can look here on the different types of sizes that we have. So generally over loose lintels, such as doors, you would have a 4x4x1/4, or if you had zero insulation, and that would be 6.6 pounds per linear foot. And that translates to 60 pounds generally, where most masons are wanting to work with a 10-foot section. And then we get to angles that are now with your insulation, that would be into the 4x7x3/8 or 4x7x1/2 inch. And now we can see those numbers here. So we went from 60 pounds to 130 pounds, or even up to 180 pounds. And we've seen many conditions actually having something that's even more closer to this dimension here, by 8x8x1/2 inch, where they're having to try to drop it down for a certain reason. And these get up to 260 pounds per 10-foot section. And you can see this in this photo. This is just a real case building, but you can see how large these angles are being welded from the structural steel frame here to the other, but quite large cavities that are trying to to withstand the tip deflection of the brick and the insulation that's on the cavity here. So now we hit that angle. As we transition from the weight of it, we're getting into the cost of it as well. And there's a couple of things to talk about. So maybe we transition back here. So these numbers are roughly, actually, it's coincidental. The weight is also, not only is the weights transition as the angle grows, this is also the prices as these angles grow. So these numbers are coincidentally roughly the price of which you would pay for these given angles. So 6.6 pounds gives you $6 a linear foot, and 8x8 inch is going to be roughly $26 or more for this angle. So these are actually references to this next price when we go here. So then we talk a bit about the ancillary costs, the buildup cost of something like this when you're specifying a standard shelf angle. So we might all be familiar with lip brick, and a lip brick is something that we've had to adjust to what we've done in the past due to these large angles. So a 1/4 inch angle, we all know that our mortar joints are 3/8 of an inch. And so a 1/4 inch angle, for instance, with a loose lintel or what we've done in the past, fits nicely within that mortar joint. But then if we start talking about 4x7 angles or bigger that are 3/8 inch or thicker, that's going to eat into the mortar joint. And so this is why we've had to adjust that with lip brick. And so this is an ancillary cost. I've heard ranges for these bricks to be $4 to $5 per brick. So this is quite a significant cost from a brick that's $1 to $2 roughly. And so then you have to think about the other things, the cost of welding or drilling these angles, and then think about the process of having to do this, potentially hitting rebar and then having to re-drill, having to re-galvanize, paint over the galvanized hole. So there's always these add-on or ancillary costs that you're compounding when you're doing something like this. The size and weight in the shelf angle results in additional costs for labor and equipment. So you think about how in the world do you get a 260 pound, up to a 260 pound angle that's going to be supported here? How in the world do you lift that? Is it men? How long is that going to take to get them to hold it up and actually put these anchors in? Or do you have a hoist or the cranes are not always usable or available, so you have to wait, and the masons have a lot of downtime. And so these all things are really just compounding, not only with the cost of the angle, but the cost of the installation of this. And so where we see it as masonry as being generally a very beneficial veneer for your envelope, these are the things that we're encountering as an additional cost. So this is the problems that we're encountering, and we'll transition into talking to some of the solutions. Andrea, is there any questions at this point in time? Okay, so solutions. So we'll talk about thermal brackets. So some people may be familiar with this. There's manufactured solutions, there's ad hoc solutions. Since we're the presenter today, we're really just going to talk about what we offer. And so what we look at here is a fast bracket, is what we call it here at FERO. But it's an offset shelf angle. That might be a more common name that you're familiar with, and what we define as thermal brackets. And we'll talk a bit about the differences of why we call it a thermal bracket rather than just an offset shelf angle, because we've added some improvements and innovations to really push the envelope forward, per se, no pun intended, to improve not only getting your angle off the slab, but also in really reducing that thermal conductivity just from the bracket itself as well. So thermal brackets significantly reduce the size of the penetrations through the insulation. We'll talk about that, but you can ultimately see here that the bracket is made out of 3/16 inch steel, and these are now punctual thermal bridges. So the only thing that's creating a thermal conductivity point are the brackets themselves. It reduces labor and material cost. If you could imagine how the installation process happens here, you would install one bracket, then you would go along continue along, and then you would install the subsequent brackets, and then you would at that point in time rotate the angle into what we call the knuckles, and then it would sit on the bottom foot of this bracket when there's it's into a masonry to masonry junction here. So, and this angle being 4 by 4 by 1/4 inch, much lighter to lift. Generally 1 to 2 people can lift this comparatively to larger angles. And we'll talk further about the adjustability with the bracket itself. And then, so also with this, as we talk at FERO, we actually provide the delegated design. So we do the engineering, we define the spacing, we give you signed and sealed packages. We take on the delegated design for this because we have all the testing, all the analysis for defining this in the most appropriate and cost-effective way. So conventional shelf angle design does not meet the demands of the new building code for sure in New York. This was introduced in May, if you're not familiar with it. And they are, so shelf angle that is bolted to the slab does not meet the new calculations. That is a fact. And many of the envelope consultants that we're working with now are asking the manufacturers, such as us, to actually provide an analysis of the bracket to make sure that it is achieving its specified U value for that location. So thermal brackets reduce thermal bridging in a wall assembly by 84%. We'll talk about those numbers in just a sec. Thermal brackets significantly reduce R values by offsetting the shelf angle. And again, we'll talk about that and how this is different from a linear thermal bridge to just a punctual location. These numbers you can reference if you're interested. These numbers can be referenced in the Morrison-Hershfield study. If you're familiar with Morrison-Hershfield, it's another Canadian thermal modeling company. They do a lot of building physics analysis. They're very influential in the ASHRAE codes. They're part of the committee that defines what is the insulation thicknesses for buildings. And they've also created in Canada, they have it's in the same pathway of Passive House, where they're doing the thermal energy demand intensity. And so this, what they reference as an acronym to TEDI, is taking the approach of saying, we only want to know the consumption of energy, not from the other systems, but purely upon the envelope. And so it's an envelope first approach. And so they've created a guide where it's an interactive guide where you can actually reference products to see what the U value, both in BTUs or watts per meter Kelvin. So it's pretty intuitive to actually have that information when you're going through your design. It's, if I can remember correctly, it's called betb.ca, or if you Google search Morrison-Hershfield building envelope analysis, you'll be able to reference that. So what we have here, thermal bridging comparison. So we have 3 inches of mineral wool. It's actually 4 inches, sorry. It's 4 inches of mineral wool insulation at an R value of 16.8. So here on the first column, we have a shelf angle that is 4 by 7 by ½ inch. And so we have our insulation here that's sitting on the angle. And so we get to 16.8 as being our clear wall analysis, whereas our modeled assembly R value is 10.8. So that is effectively reducing the R value by 36%. And so what you see here to point out is not only is the reduction of the energy loss, energy loss or thermal conductivity is not a two-dimensional anomaly. It's actually a three-dimensional anomaly. And so what we would think initially is that the energy loss would just be in this location here where the shelf angle is, but it's actually degrading the insulation's performance as it's going to find its delta point. So it's affecting it above and below as well. So these are areas where it's degrading the insulation, not just here locally, but across the facade of the building. So here, then we still have the same benchmark at 16.8 for our clear wall value. And so now we can start to really take a look into how this is different comparatively to a shelf angle. And so now we have our insulation here behind the angle with a 4 by 4 by ¼ inch angle. So now we have as close as possible to nirvana with reducing our thermal bridging by reducing the surface area of this, this mass of steel. So we have it all behind the angle, and now we only have a punctual thermal bridge here at this location. And so we're looking at 3/16 inch steel comparatively to even the angle at a ¼ inch or here at a ½ inch. And so we have a benchmark of 16.8. And for Morrison Hershfield, our model R value assembly is 16.7, which is an effective reduction of 0.6 for this location. So this is actually really phenomenal to actually be able to achieve these numbers just with by simply getting your insulation behind the angle and having punctual thermal bridges at these locations. So one of the important things is to talk about adjustability as well in this. So what we want to talk about is, okay, now we've gotten through the thermal bridging, but we also want to know how do we get adjustability within the bracket, because we know the only straight lines that we've ever seen is the ones that are generally on the drawings. When we get to a job site, the slab is out of tolerance, both up and down. It might have turtle shells. It might have tolerances at the face of the slab that you all have to really account for when you're now taking the intent of the design and it's being applied at the job site. So with the fast bracket, we have here, as you can see, that there's the slot for the vertical adjustability. This is a slot that's 1 3/4 inches. In New York, it's commonly anchored with a wedge insert that's has a 3 3/4 inch askew bolt. So this would give you an adjustability of 1 inch up and down. And then we have shims that are full height shims for the bearing area of the bracket. And so you can now add shims. One thing to point out here in this point is that when we step back and talk about the delegated design process, we also go through the chain of creating a submittal. Once that submittal is approved, we send fabrication drawings to the mason for him to identify if there's any areas that's in the slab that's out of tolerance, because the brackets themselves as a standard are made at ½ inch increments. But if there's tighter tolerances that need to be accounted for, these can be made specific to size. And so if say the slab was 1 inch out of tolerance in one location compared to the other parameter, we can make one bracket or a series of brackets 1 inch deeper or 1 inch shallower here. So these brackets adjust based upon the insulation thickness and also the tolerances to the job site. And then any small deviations of the tolerance of the slab can be adjusted with shims behind it. So other thing is that we might be familiar with is, well, we're talking about the depth and how we adjust for the depth, but we also have to think about the height, because not always are the slab transitions going to be at the location of the slab, but they may be further down. So as mentioned, the bracket can be made specific to size. But also the bracket or the offset shelving system can be made to any height as well. We've actually done projects in New York that these brackets have been up to 5 feet long. If you go to our LinkedIn page, we're doing a project currently on 378 Weston Avenue that has brackets that are 3 feet tall in some locations, and some of them are as deep as 12 inches. So there's a foot deep and 3 feet tall. And there are variations back and forth through different locations. And there's some really nice photos to take a look at our LinkedIn page if you're interested in taking a look at those. So this is what we would describe generally as a masonry to masonry condition, where you have brick below and then you have a slab here at this location, and then you would have masonry above. And so one of the things, again, with the way that we approach the market as an engineering firm that provides facade connections, in this case masonry, is that we will give you the spacing. So not only are we going to tell you the types of brackets to use, but we're also going to give you the spacing. Commonly, it's 4 feet on center. Sometimes it's more. It could be, sometimes it's less, but it's really based upon the brick heights. And the brick height will determine the spacing of the brackets themselves. So if you go to our website, there's load tables that you could actually reference for your design, but we would prefer to offer that to you as a service. But so if you can determine your brick height, you can ultimately determine the spacing of the brackets. Now, so one thing to point out, generally the brackets are not the governing thing based upon the spacing. It is the anchor. So the anchor is actually the weak point in this design. So that's one thing to consider when you're designing, is what type of anchors that are being specified. Generally pre-installed anchors function better than post-installed anchors due to the pull-out capacity. But we would be providing the anchor design as well if required. So this is something that we can also offer. So this is a masonry condition. So we have here your slab. And so we can look through this detail quickly. We have our membranes. So we have our control layers. We have our turn bar here somewhere is located. We have our bracket. And then from your turn bar, you have your flashing that would come down, and then your membrane would come onto the flashing that's now going down and over the bracket, and then that to the face of the angle, and then onto the horizontal leg of the angle over the top of your drip flashing here. And so you can see here in this section, this is what it would look like, where you would have your mortar net for your droppings, and then you would have your control layers here over the bracket themselves. So here's a condition where we talk about the brackets being longer, but also transitions over windows. So one thing to point out is that when we have transitions over windows, there's 2 different ways to address this, and it's really dependent upon, again, the spacing of that window and the brick that's above it. So if the window is a larger window and there's a significant amount of height to the brick that's over the window, we would have a lintel bracket here. And this is what you see in this rendering and the section detail. And so I'll start with the section detail to just kind of point out the difference here. So a lintel bracket is intended to have the angle flat. That would commonly look where you would look under, if you were in the building and you were looking up, you would have a nice clean angle here. Some people might say that this window should be pushed back. We see that commonly in New York, and we see that commonly addressed with ornamental trim, or we can also provide a return angle that they would have a structural angle here that would support the brick, and then there would be a return angle that would hide the underside of the bracket and the insulation. But there's various different options here, and if there's a project that's looking for this for specific detail, we can offer those options. But in this case, we have a bracket that's coming out from the slab edge down to the window. And so here you can see this is a long extended bracket is what we call it. And so now you have your through wall flashing going over the bracket that would still go down along the perimeter, down along the face of the bracket and onto the angle. And then you would have your mortar net into your cavity here. So this is the transition over the window and then how an extended bracket would look. So in the event, for instance, that there's not a lot of brick in this situation, what we would actually do is that we would skip windows, what we call skipping windows. Pardon me. And in skipping that window, what we would do is we would have a standard bracket located here at the very perimeter of this masonry wall, and then at this location, and then where the masonry would pick up again, we would have another bracket. And so you wouldn't have need for a lintel bracket over the window. It would just actually span over this window here. And so again, being that we offer the delegated design services, this is opportunities where we can identify these things and how to save money. In this detail here, where you can see that the angle is punched through the back, whereas comparatively you see here that the angle is actually being supported by a foot, and this foot is now in the back of this angle. We approach this more as a systems approach, where we punch the angle at our facility, whereas here, this angle is bought locally and we only provide the brackets. So here you can see that how your flashing would come down from above over the brackets here. You can see there's a bracket behind it, and then it would transition over the face of the bracket down again onto the shelf angle itself and onto your drip flashing. So alternative options. So this might be an area where you have a different veneer transition. So you might have a stone or stucco, an EFA systems, for instance. And so, and then you have veneer, or you might even have louvers, for instance, or something here where there's just not a clean transition, where the bracket wouldn't be able to support it in this manner, but you would actually want to flip it over. And this is an inverted bracket. And so now for instance, if this was an EFA system, the EFA would be integrated with the bracket itself, and then the angle would be inserted here through the top of the bracket, and it would support the brick here above it. And so this would be an inverted bracket where you have veneer transitions. So different types of brackets, as I mentioned. So the standard bracket here is the bracket where we only provide the bracket. The angle is bought locally. We don't provide anchors. We can, but we generally don't supply them. We allow you to buy those locally. Whereas with the lintel brackets, we would then provide this as a system where we would punch the angle to have the foot inserted into the vertical leg, and that would be the lintel bracket as a system. So there's some, oops. So there's some other ancillary options, things that it would come with the package. There's shim plates, generally 10% of the amount of brackets that we would bring to the project. And then there's locking pins. And these locking pins you can see here, are inserted one per angle. And this is just to make sure that the angle doesn't pop out once prior to brick being installed on it. Once the brick is installed onto the angle, these pins are no longer necessary. It's just a matter of quality control that the angles don't pop out prior to the brick being installed onto the angle itself. So everybody wants to talk about cost. I'm sure you've been through many presentations where you thought you've heard of a great product and you want to talk about it for your next project. But when you get to the question, well, how much does it cost? You hear the question that presenter talking about ROI, and it's really waffling about the question, not giving a direct answer. And I always have the belief, when it's coming to people's money and the green movement that we live in, is that many of the people that we are working with, the most important green thing that they're encountering is the things that's in their pocket, and everything else comes afterwards. And so we actually, at FERO, we actually have a pretty compelling case that we're actually cheaper the day that the mason buys the product. And so these are live pricing models. So a 4x7 by ½ inch angle that you would need for the insulation type, that angle is $21.25. And then we have comparatively thermal brackets. We say that this bracket comparatively for these two conditions is $24 a bracket at 4-foot spacing, which would give us a $6 per linear foot bracket price. And then a shelf angle, which is a bit on the high side in my opinion, at $7.25 per linear foot, would give us a total of $13.25 per linear foot. So we're at $8 to $9 per linear foot on price alone, or product alone for installation. So then we look at cost savings for extended brackets. So we have extended brackets here. So in these extended brackets also, we can eliminate kicker systems. We have a specific solution that can eliminate the kickers that you are commonly having to your engineers designing. But conventional, so we have here, what we see is a tube section that comes down, a knife plate system that's going to hold that's going to weld to the angle itself, and then the Nelson studs. And we see a price we've encountered at $95 per linear foot. Whereas compared to this one with the same depth, and length or height, along with the angle, is $32 a linear foot. And so keep in mind one thing as well is that you can see here, we actually, by using this system, you're actually getting rid of the drop beams that you're maybe familiar with, if that's the case. So alternatively, we see that an architect would create this as a drop beam. And so when you have anything that's not a flat slab for a form worker, that becomes very expensive. And so this is also eliminating a drop beam that reduces that cost. And we've heard some really into the tens of thousands of dollars of how much that fast brackets have saved by just eliminating drop beams. So additional costs that we talked about, so installation. So we think about just the weight and sheer size of lifting it. The lip brick that you can remove because you're using a 1/4 inch angle that fits nicely within that 3/8 inch mortar joint. Lower cost for the shelf angle as well, just by itself. And so thermal brackets can also span the cavity. So smaller size shelf angle can be used, less freight. And so this goes into the freight and cost of things. And so those angles can be sourced locally rather than having to find a steel fabricator that's going to have to take bent plate and actually bend these angles. So no welding or drilling. This is just a mechanical connection, which would lower those steel. So now that reducing the welding or drilling is reducing an extra trade that we commonly see as a steel worker out there. We work mostly with masons to have this installed. So now it's one trade, one installation, less time and fights and arguments of how it was installed improperly from the welding or installing the angles. And now masons are in control of their installation. So this is also reducing the amount of scope differences and installation tolerance differences that are on the job site. So we'll go through some different applications that may be interesting. So there's, you might be familiar, you might encounter thin slabs such as composite deck systems, Pandex, there's various companies. Due to the thinness of the slab, what we would do is anchor to the top of the slab. And so you can see that we have an attachment that fits into the track itself, and then it anchors to the bracket. We've done this with a project in New York, Joseph Adabo. If you're interested, we can send some site photos for this. As we talked a bit about it, the inverted bracket, and also hanging it from steel sections. So this one is a W section, where we see it quite often going through tube sections, and it can be bolted, it can be welded or drilled through the tube sections, use hollow bolts or Lindapter bolts in tube section applications. So there's really not an application from a backup wall or from a structural condition that can't be used. We do it through CMU blocks. We generally see the preference to be where it's drilled completely through and it's through bolted. And so there's various options for any types of projects. We'll be doing a CLT building coming up soon at Princeton University, where we're actually going to be working with CLT there. So double brackets. So we get into some situations where we have to create some unique things. And so again, being that we are engineers that create masonry connections, we can create things like this. So imagine that you had different transitions. Projects, again, such as 378, where the brick comes down and then steps back and then comes down again. We can create multiple different systems to support that. So double brackets in these locations. We also have another product called Fast Flex, where we augment the angle. And so this comes in combination with the fast bracket. And so we augment the angle, and then it can be flexed along a non-squared geometric shape. So if you had a curved wall, you would be able to actually augment the wall with the angle itself. And this is generally a very difficult thing to do with brick, but we can do this pretty effectively, and it's worked out well. We also, a project that's ongoing currently as well, if you're interested, passing by 2505 Broadway, where this is actually this angle. And so these are custom angles that we've manufactured to match the pilasters of the columns that are in the building. So these were running up the whole facade, and the brick starts, curves, and then it steps back, and then it does the mirror on the other side. And so also, if you're wanting to have a more masonry reveal above your windows, this is our masonry concealed lintel clips. And so the way that this works is that you would have a fast bracket, and these clips actually hang onto the back side of the angle, and they come down, and then you would install the brick as it's being installed through the rebar. And so this would be hanging those the brick for your hidden soffit here. And this is, we've done this on quite a number of projects in New York. So if you're looking for references, we can send you the renderings such as this, or reference projects. So some of the things that we can talk about as we wrap up a bit is some of the thermal brackets that you might be familiar with in the comparisons. Just to really point out some of the differences. So we see these common details. We define these are more of ad hoc solutions or on-site solutions, where they take a tube section, they cut it, and then they drill it through, and then they weld it to the face of the slab. Again, now you have multiple trades. It's actually quite expensive, and so there's no adjustability. This is a knife plate solution where they actually cut the angle, and so now the angle, one of the horizontal legs, is anchored, and so again welded, and now this is a fixed system on the site. So this has to all go up at once rather than having to be installed, the brackets being installed individually and then the angle going in afterwards. So there's really no adjustability in these things. The engineer of record would have to also engineer this, so there's nobody that's going to come from a manufacturer that would provide you this solution. So here's a project that's a big project in Canada that we can use as a reference. So you can see the thermal brackets, and you can see here, and you'll see in the following photo, the difference of what even our previous generation brackets look like versus what they look like now. And so one of the things last year we did as an innovation was to reduce the thermal conductivity even further than what we had previously. And so the way we did that was we actually punched out any of the superfluous steel that's here on the side of the brackets. And this really reduced the thermal conductivity to the values that you seen earlier in the presentation. And so people ask from time to time, can we use pads or things like that? And we actually went through those studies looking at different like plastic pads, or we even evaluated aerogel. And with those products, there comes along a lot of caveats that you have to consider. And we'll talk about those in the next slide. But as you can see here, the comparison with a manufactured bolt-on solution versus fast brackets. The brackets go on first, they're installed at once. You can use any anchor that you would like, be it post-installed or pre-installed, and you have a nice clean solution. Whereas here at the one at the bottom that you may be familiar with, this is a welded solution. So these knife plates are welded to the angle. The angle has to be bought with the system, whereas with fast brackets, the angle is bought locally. And so this all has to be installed at once. So the knife plates have to be installed in unison because they're welded together onto this track. And most manufacturers require you to buy these anchor channels of the tracks as well. Whereas we say buy any of the anchors that you're commonly familiar with or you have a level of comfort with. All right. So yeah, as I was mentioned just previously, the pads. So we had people ask this question: should we use pads, or should we use some kind of other non-metallic material? Because metal, as we've spoke about, has the highest thermal conductivity. And what we found is actually getting rid of the superfluous steel is the biggest result in reducing the thermal conductivity. Whereas with pads, we really don't know the compressive nature of this material. You're also making this bolt longer in the cross section of the anchor. So now by increasing the bolt length that's exposed in the cross section here, you're inducing eccentricity on the bolt. So these bolts have to be increased per location. So now you have more anchor locations. And if you're interested, there's a Northeastern University did a study with pads, and the study actually came to was that these pads to get back to zero effectively, that these pads have to be an inch or thicker. So you're really having to look into a thicker pad, whereas you're really not solving any solution by having a really thin pad and having insulation on this angle, because the angle is still the same depth, the same dimensions, and pardon me, and also the same thickness. And by not having this offset enough, you're actually potentially creating a bigger thermal conductivity location in this area. So some projects that we've done in New York, I think last time we've tallied up, we've done 1,500 or 1,600 projects across North America. We have a partner dealer with Glenwood Mason Supply located in Brooklyn. I think I don't know if I had to take a guess, we're closer to 40 or 50 projects this year. But here's some of the ones that are interesting and people that might be on the call. maybe you are familiar with one of these buildings. We do have 2 open spaces here for some new projects for anybody that's looking to specify fast brackets. But yeah, so there are some really nice buildings, and so we're doing a passive house that is planning to be passive house project currently at 425 Grand Concourse. This would be the, it's being planned to be passive house. We'll hope, fingers crossed it will be. 1350, sorry. So projects across North America, various locations, and if you are going above the 49th parallel, or we have colleagues there, there are some other projects. And so we do a number of projects that are different scales, different sizes. People ask the question, well, when is a good idea to use fast brackets? And I would say that if a building is 2 floors or taller, that's when you would want to start considering fast brackets. For buildings that are 1 floor or maybe even 2 stories, generally you can get away with using loose lintels on most of the connections there, or locations there. But that's where and if it gets above 2 stories, that's when you're looking at structural connections for your masonry supports. And so this is when you would get us involved. We have, again, the capability of defining not only the spacing of the brackets, is there a possibility of even skipping floors, which reduces the thermal conductivity even further. So these are just really the add-on options when you're soliciting us as a delegated design partner for these buildings. We can give you solutions that if you're to identify what your path of what you're trying to achieve, be it passive house, or if it's cost conscious, we can help with those things. Again, some adjusted reference of projects. So again, we do for everything from cast in place to anchoring to CMU to steel to hollow core planks. There's various options. If you're working with any project, there's really a solution for all of those. Just wrapping up quickly, we also manufacture masonry ties. These masonry ties, if you want to look into it further, we have brochures, but our masonry ties have been tested to be the lowest thermal conductivity masonry tie that you can get on the market. And the way that we do that is by punching the holes through here and actually the thinness of the metal. So again, those 2 variables, surface area, we can space our ties out 16 by 24, reduce the amount of material, and the thinness of the steel actually reduces the mass. And so these are the things as we wrap up that we can talk about. But here's a comparison. So you might be familiar with these self-penetrating ties. And so you can see the values along this at so the assembly values. So we get to 0.050 compared to 0.051 in these locations. Yeah, and so I think the presentation will be shared, but there's plenty of other things that we can talk about, but I think this is the time where we'll stop the presentation and take any questions that might have come up throughout the presentation now.
Thanks, Adam, for your presentation. We have a little bit more time for taking some questions, and Andrea, maybe there's quite a lot of questions in the chat, so since you already answered some of them, maybe you take some of those questions.
Absolutely. Thanks, everyone. These are really great questions. So I've endeavored to answer as many as I can in writing, and so I've just made a list here of a few that I think are the more frequent questions, and maybe that I haven't gone into as much detail on. And so, Adam, one of the questions, and you spoke to it, but maybe you could speak in a little bit more detail, is that's come up in a bunch of different ways. Is can you use a composite pad or a thermal pad in conjunction with the fast bracket? And I think, obviously, the answer is yes, it can be used. And I think maybe you can go into a little bit more detail about the thermal modeling that we did to show that, because we really wanted to evaluate it ourselves. So maybe if you could speak a little bit more to that. That was a frequent question that came up.
Okay.
Then,
yeah, and that's a common question, and I think people generally tend to see that the pads are available, and because it's a composite, we assume that a composite material would improve the performance of a non-composite or a metallic product. And so we had that question quite a lot coming up, and so we worked with Morrison Hershfield and RDH to evaluate what's the best path to reduce the thermal conductivity based upon the thermal conductivity for the standard product. And We evaluated pads at varying thicknesses. We evaluated aerogel, which is a coating as well. And those results actually came back pretty surprisingly. And so when we made the bracket here a thermal bracket, whereas previously the steel was solid here on the sides. And so taking the pad, putting it behind the thermal bracket, the result was a 0.03% improvement. So 0.03 from that, from the slide that we talked about, of that 0.6% reduction. Our bracket is roughly $24 for the bracket that you see here. And as we understand that these pads start around $15 based upon a 1/4 inch thickness or half, and they multiply based upon the thickness and the amount that you have to buy. So from that perspective, I would say that, you know, we already, from the bracket itself here, there's only a 0.6% area where we can actually improve on. And so then from that 0.6, there was only a 0.03 improvement. So at that point in time, there's really not a lot of juice to squeeze out of this detail any longer. And then you couple that with the cost of the pad, and then they add it on with the engineering, because this bolt will become longer and it induces eccentricity on the bolt, and you have to potentially add more anchor locations or more brackets or more of these pads. The price really starts to become not economical, and then the improvement is not economical either. So from that perspective, we don't really see pads being the right position. If you're interested in doing that, we wouldn't push back on that. We would be a bit concerned about the anchoring detail, but we would communicate those with you as the design progresses.
Thanks, Adam. I think that's a great summary. Another question that came up frequently is what's the maximum length that you could see a thermal bracket drop down? And so we've discussed in the chat room that, you know, there's no real maximum, and that our engineers design it frequently. You know, the question that comes up is when are kickers required? You know, and a lot of questions around that. And so maybe you want to speak to that a little bit more.
Yep, great question for the people that's asking it out there. So yeah, we've done brackets as tall as 5 feet. So imagine I'm 6'6", so I'm a pretty tall guy. So 5 feet's right about here somewhere. Or probably more about here. So that's a pretty tall bracket. And as far as the alternative to kickers in this situation, so this is a good slide to reference that, is that extended brackets that come down to these locations, if from the anchor point to the bottom of the bracket itself, if this bracket is from anchor to bottom is less than 24 inches, there's no additional bracing that would be necessary. Beyond 24 inches is when we would introduce the brace that's anchored to the back of the bracket. That would be inside the pocket of your track wall system here. So it would actually fit within the track. And so it would be bolted here, and then it basically rotates within the pocket of your stud wall. So there's no kickers on 45s that are sticking out where you have to have drop downs or some kind of fur down to hide those traditional kicker reveals.
Thank you. A great question that we got asked is that some jurisdictions are requiring that project-specific thermal modeling per facade is submitted with the buildings. So the question that we got is this something that FERO can do? Do we work with the architect? What can we provide?
Yeah, that's a great question. And we've seen that as well recently. And actually, yes, we do that. We actually will provide the thermal modeling analysis for the specific location of the fast bracket. And one of the things that we've actually encountered is that we do have standard details of the thermal modeling for a given bracket. But as you can see, that these brackets can change in heights and depths. Yeah, so you can see that this one is a much shorter bracket compared to this one. So the thermal modeling for each of these brackets would be very different. And we model to that bracket itself. And so what we work with Thornton Tomasetti both in a structural capacity and also an envelope capacity. And that's what we do for them as an example, is that we give them project-specific thermal modeling analysis for the given brackets that are on the building.
Great. We got a few questions regarding flashing. What are we typically seeing when when people are flashing with fast brackets. And I think we have a detail that you've gone over, but maybe you could speak a little bit more about some of the different things that we see.
Yeah, I think there's a lot of different options that we see we're flashing. I think this is probably a good photo to reference here. So here you can see that they have their membrane coming down. There's a termination bar that's attaching their through wall flashing here at this location. And then it's coming down and over the bracket. And then there's a transition of another through wall flashing that's come at the bracket itself, coming down onto the angle and into the drip flashing. So this is a flashing manufacturer that's rolled this this very thin through wall flashing. We don't see that the price is much different from this compared to going straight down and over the angle. The overall dimensions of the flashing is not very different as far as the amount of materials necessary. So this would be a common flashing detail. But there's different products and there's different options as far as flashing. We have some common details. So the people that are looking for something like that, please reach out to us and we can provide those. There's products like this I can show you. I think that this is a really innovative product in and of itself. It's a product from York and it's adhesive. It actually has got an adhesive to the backing through wall flashing. And so you can see it's pretty thin. It's puncture proof as well. And so then you can actually adhere this onto the wall, comes down onto the insulation, over the bracket, adheres to the angle, and then you roll it down. And so this is all really pliable, and you can actually roll this without actually having to have somebody bend this. So there's different options as far as flashing, and we can provide those to you if there's a project-specific question.
Great, Adam. We got a few questions, and I'll just summarize them. Just basically about attachments, and can fast brackets be attached, to steel, and how are you doing that to wood backing, and how are we doing that? And I think the short answer we've given over the chat is any place that shelf angle can be used, fast brackets can be used. We see a number of projects with wood, steel, CMU backing, but maybe you could elaborate a little bit on that because there's a lot of questions.
Yeah, so as far as I'll start with the steel one. So as you can see here, there's a steel one. This is a W section. So there's a clip attachment to the top of the flange. If it's a tube section, so like a hollow tube steel, there's a couple of different options. You can drill through the tube. You can weld it to the face. That one reduces the adjustability. So we don't recommend that as the first option. You can weld Nelson studs to the face of them and use that as a threaded Nelson stud to the face of a tube section. Or my personal recommendation is Lindapter hollow bolts, where you drill a hole and it's an expansion bolt for steel connections. As far as CMUs, we commonly see most new projects in New York, all the CMU blocks are filled and grouted. And so what we see there is either through bolting or some form of an expansion anchor by Hilti or Power. And then for cast in place, it's really the general ones of pre-installed anchors such as wedge inserts that we see commonly for in situ concrete, or post-installed anchors, again with Hilti or Powers. So as for wood, it's a different application, and again, it's always going to be based upon the spacing. So we'd either anchor the top with the clip attachments, and depending upon how the CLT is laid out, you could potentially anchor to the front. In some situations, we actually see that they put an CLT slab, and then we anchor the bracket to the angle that's effectively supporting the CLT.
The remaining questions are mostly related to specific details, and have we seen fast brackets used in projects like this? And so what I've indicated to everyone is that yes, we with fast brackets being used in over 1,600 projects in North America, we've got a detail or an example of every type of scenario. And so there's a lot of requests for information to be sent separately. And so I will endeavor to get that out the door today.
Yeah. If there's project specific ones, we would also be interested in you sending us a detail. We get that question quite often of how do we solve this problem? And we'll give you a section detail back basically within 48 hours at the most. And so this is this is how you would solve that problem. And there's been very few times, I think I can account for one or two maybe, that we said, hey, there's really not the best solution out there amongst those 1,600. So there's a track record for a lot of projects that we have found solutions that might not be the most straightforward that we've talked about as well today. Obviously, we have to talk, due to the time constraints, talk about generics of what we see most commonly, but there's always something that we can create as a speciality for projects, obviously things like this.
Really would like to thank everybody's for their attendance and for the great questions. I hope I tried my best to keep up to them all. And if I've missed any, I'll get back to you individually.
Yeah, I think Andrea, you did a very good job, and thanks for Adam for presenting. You guys, that was a very interesting, I think, presentation. And from the chat, from what I can read, everyone got quite a lot of information out of it. So thanks for presenting. Thanks everyone for joining us today. We'll work on a new event schedule for the spring season. So please join us on the newsletter or as a member and be part of that conversation. So thanks, everyone.
Thank you, everybody.
Thank you.
Thank you. Bye.
Bye now.